right, so hello everybody. I hope you can hear me. My name is Peter, and I want to guide you today through the webinar, which is understanding child psychology with eye tracking. And we have a bunch of great speakers today that are already here with us. Some will dial in a bit later. And yeah, I also especially want to welcome my co-chair, Julian, here today, because it was kind of our idea to do something like that almost 2 years ago, right? When we thought about doing it. And then, as you all know, the pandemic hit us. And even though we did a lot of things online, yeah, we needed to get going and get used to the situation. So therefore, we pushed back that project. But therefore, I'm even more glad that we could start it now today to talk with all of you about this subject. Just some housekeeping. So you can write your questions always in the questions section. So then we will start answering them along the way. But also we will have some time in the end so that we can have a bit of panel discussion, so where you can ask everyone basically the same questions, and then we can bounce back ideas back and forth. But of course, you can always specifically address questions to the speaker that is speaking at this very moment. But don't worry if you maybe get in a bit late. We will record this session and then make the recording available for everyone that signed up. And I can already say that more than 400 people signed up, which is really amazing to see that a lot of people are interested in this topic. But I think most probably that is due to all the great speakers that we have here online today. So thanks a million for making that happen. I don't want to lose too much time and then hand over right away to our first speaker, which will be Robert Hepach, who is Associate Professor of the Department of Experimental Psychology at the New College in Oxford. We know each other since quite a while now, because you've been in Leipzig before, and I remember that as it has been last year, even though it might have been already 10 years ago, where we saw each other in Leipzig and had some great eye tracking workshops. So I would say I hand over the microphone to Robert, so he can start with the presentation.
Great, thank you very much, Peter, and thank you also for Julian for organizing this and for inviting me. Since you said handing over the microphone, can I just triple check that everyone can see the slide okay?
Yeah, we can see them very well.
Okay, great. So again, thank you very much for organizing this, for inviting me. When it comes to pupillometry, it's both a fascinating but also a deceptively simple method. And all I would like to do in the 20 minutes ahead is to give a brief overview of how the field of pupillometry has developed in developmental psychology. I should say that when it comes to pupillometry, I am a user, and I have been a user for 14 years. I've experienced the highs and lows of this method. It's a deeply fascinating tool to study cognitive development and emotional development, but it can also go horribly wrong if one uses it with false expectations and misguided assumptions about how this all works. And since I'm learning myself every day new things about the method, what you're going to see from me is not based on my personal judgment or reflects my opinion, but it's based on a review. In a review of what I think are all the studies published since 2007 until 2022 that have used pupillometry to study a developmental population. So I've tried my best to minimize the few things that I thought stand out if one looks at the entirety of the work published so far. And I wanted to simply share 17 things that you may already know or that you may want to know in case you're looking into using pupillometry in one of your studies. So assuming that everyone can see the second slide, okay. The first point I would like to start off with is by pointing out that the underlying mechanisms of pupil dilation are quite well understood as they can be for any empirical science. And this is owing to research with adult participants, but perhaps more crucially with non-human primates that have pointed to a structure in the central brain, the LC structure that you can see with the blue dot on the very left-hand side of the slice image of a monkey brain. And as you can see from this from the schematic, it is that particular nucleus that has caused all the pupil dilation researchers so much fascination, because it is reliably correlated with pupil dilation size changes. So the more active this structure becomes in states of high alertness, the more pupils will dilate. This is based on seminal work by Aston Jones and colleagues. And you can see this from their famous graphic on the right-hand side of your slides, this correlation between activity in this particular set of neurons and the subsequent almost concurrent change in pupil dilation. And again, on the left-hand side, the right image of the brain points to the most recent insight from this research group, namely that there are different parts of this LC component, each of which are sensitive to changes in arousal. Some of it are more sensitive to changes in cognitive load, as it were. So on a neuroscience level, this is all very exciting, and it really forms the basis for why we as developmental psychologists think that measuring pupil dilation is a good way of measuring attention or cognitive load. And I'll come to the details in just a second. The second point to be aware of is that psychological mechanisms are only one of many factors influencing the signal. So in my cumbersome schematic, you will see that at the very bottom, luminance changes affect the pupil bidirectionally. So an increase in luminance, bright stimuli will constrict the pupil. A decrease in luminance will dilate the pupils. And in addition to these luminance changes, cognitive processes such as attention or changes in arousal can in addition dilate the size of the pupil. So it's very important to keep this in mind, that this is only one of the many factors influencing the size of pupil. It has profound influence on how we design our studies, something I'll come back to in later points. Third point is just more of a terminology, so also to make the following slides a bit more hopefully understandable. So by pupillometry, I mean the science of studying systematic changes in pupil dilation. Pupil size and pupil diameter essentially provide the same information. They provide information about how large the pupils are at any given point in time. Pupillary oscillations reflect the continuously changing size in pupils, and pupil dilatations are the recurrent increases in pupil size over time. Whereas pupil dilation is typically used to single out an event increase. So much as in ERP research, this would be a single event increase in pupil size in response to a specific stimulus averaged across many trials and many participants. And the pupillary light reflex is an involuntary decrease in pupil size in response to a bright stimulus in visual focus. And the reason why I've singled out pupil dilatations and pupil dilations here is because, for all we know at this moment, psychological effects can only dilate pupils. There is no evidence that there's any systematic decrease in pupil size as a consequence of a psychological effect. Fourth point, maybe most relevant to the webinar today, is that pupil size can easily be measured with modern eye trackers. I'm not telling you anything new here, but I would like to point out that this is in itself not yet data. These are just numbers for every sample the eye tracker takes. And it's a whole different business of how you actually get from those numbers to drawing conclusions about psychological mechanisms. But it's a good entry start for us to know that these eye trackers can collect this information readily. The fifth point is a point on methods and design, and that's that the developmental psychologist's standard participant is really any experimental psychologist's nightmare. So what you see here would be the ideal setup of running a study where you measure pupil dilation. And you might not be able to see this properly, but here is actually the child sitting on their parent's lap. And this red dot on the left-hand side is a dot that you have asked the child to focus on, such that their gaze is as steady as possible in a controlled dark environment where there are no other artifacts on pupil size. And ideally, in this dark environment, you would present your stimuli auditorily, just to further avoid any effects of luminance. So this would be the ideal scenario, and actually that's the setup in which many studies with adults were conducted. After participants were asked to sit still for several seconds to a few minutes to have any sort of stress effects dissolve before the study starts. And I'm putting this up here just to point out that any deviation from this, any alterations you have to make in order to make your study engaging and ethically permissible for a child participant, increases the burden on you to make sure that any effects you do find are not a consequence of luminance artifacts. Because it's important to bear in mind that even in these dark environments, pupils are constantly oscillating. It's taken from a review paper from my colleague and myself from several years ago, where what I've plotted here is the time of stimulus onset for 30 seconds plus, and just plotting the change in pupil size as a function of in the units of millimeters across time. So it's a fairly, as it were, ugly signal where the pupils are dilating, constricting, not in any particular systematic way, but this is what you're looking at if you were ever to plot raw pupil size data in your studies. So just bear in mind that this is a constantly evolving situation. Anyone's pupils are constantly changing in size. And there's typically 3 levels of analysis that are relevant to pupillometry researchers. And quite curiously, most of us will not really wonder too much about level 1 because we go into a study thinking about level 3. So let me walk you through these levels very briefly. So the first one is the signal. And this has to do with how do you get the numbers that you've collected in this eye tracker file into an actual dependent measure that you can statistically analyze. So the first level has to do with all these nitty-gritty of elements of processing data, deciding on time windows across which to average your data. And this is a whole philosophy in and by itself. The second level is one where you have to provide some kind of evidence in your study that the effects that you have found are not a consequence of luminance artifacts. So how sure can you be that what you've measured is actually a psychologically induced pupil dilation effect independent of luminance effects? And this can be quite tricky. And you'll notice that many studies using this method with young children will have some mentioning of how the authors ensured that there weren't any luminance effects or that luminance effects were controlled for. And there's various techniques one can use. I'm happy to elaborate in the discussion time. And then finally, maybe most interestingly, this is what gets us sort of excited about this method, is the actual psychological mechanism, because we would like to study memory, cognitive load, surprise, right? All these really cool, rich phenomena, but they're always the third level from these levels of analysis. And it's important to clarify that there are these 3 levels and that one can have lengthy discussions and write dissertations about each of those levels. And it's quite helpful as you're communicating your finding, or as you're inquiring about somebody else's finding, or as you're criticizing someone else's finding, what level it is that you're referring to. Point number 8, the signals. So just to point out again that this is a philosophy in its own right. And the question is, how do you get from these numbers in these text files, 1 number per sample? This can add up quite quickly if you have a high sampling eye tracker. How do you get from this data to something that has this at the very bottom part here of this center figure, the bottom part showing this pupil dilation peak the typical shape of how one would analyze these pupil dilations in studies. How do you get there? And thankfully, I don't have to tell you how to do this because there are these wonderful projects such as the Time Studio project that provides an interface, a very intuitive interface of where you can upload your data and run through the various processing algorithms. So this is, again, a science in its own right. And luckily, our colleagues, Per Nyström and his colleagues, have looked into this for us. When it comes to evidence of psychosensory stimulation, I do want to point out that probably the Bible of pupillometry work is a book quite fittingly called The Pupil by Irene Löwenfeld. It's pretty a heavy book, so if you're looking to borrow it from a library, just be aware it's over 1,500 pages. And I just want to use it here to mention that you can study or you can spend your entire career studying the pupil with all its fascinating elements without ever really so much wondering about the psychological mechanisms involved. So there's so much going on and so much that goes into systematic changes in pupil size that I think is always quite humbling to be aware of this research and to always reflect and ask oneself in each of your studies, have I done everything possible to make a strong claim about a psychologically induced effect in pupil size? And so this online catalog here I've put up and the web link at the bottom is really fascinating with all these different sketches from the authors. So I'm just using here as a reminder that this is an actual step that every study will have to progress through if they're wanting to make claims about psychological mechanisms. Point number 10 would be the actual psychological mechanism. So this is what as I said, probably gets us all excited about using this method. And what you see here is my futile attempt at using word art, where I've essentially taken all the 93 studies I could find published between 2007 and now, and try to summarize what the authors in each study, in their discussion, in their conclusion, state what they think pupil dilation differences reflect. So you might not be surprised if you've worked with the measure or if you work with adults, that for the majority, attention, arousal, cognitive load are the sort of classic mechanisms that are being picked up on. And if you're familiar with these word arts, you'll gather that the larger the lettering, the more frequently this term was investigated. So just to give you a flavor of the richness of the kinds of mechanisms under investigation, but also to highlight that the sort of big three in all of this are cognitive load, sometimes also referred to as mental effort or cognitive processing, as well as arousal and attention. As an 11th point, maybe just to also cut the research sphere in developmental psychology in a hopefully helpful way, I just wanted to point out that given this review of the studies published, there are really three main areas of research in which developmental psychologists are active. The first one is what I've labeled here surprise and violation of expectation paradigms. So these are studies that look very much the same as looking time studies, where you're measuring a response to a surprising event and compare it to a non-surprising event. And you're interested whether these unexpected events lead to any increase in pupil size. So the logic would be similar to looking time studies. What is being measured is so-called task-evoked pupillary responses, and the sort of phasic changes, so immediately following the unexpected event, is what we would be interested in analyzing. The second broad block is studying task-evoked pupil dilation and neural activity. So here the idea is using the measure of pupil dilation similar to how one would use other measures of central nervous activity. So where the brain, the system, the participant becomes sensitive to certain changes in the environment. I'll illustrate this in a second with this specific study, but this can take a different shape than classic looking time studies, which typically present some kind of static resolution, which is expected or unexpected. But in the second domain of studies, this can really be research where the presentation is a bit more dynamic, and you're trying to pinpoint what it is about a specific stimulus and this could be a video stimulus that gets the sort of system engaged and results in greater attention. And as a sort of third block, there's a sort of research on arousal state and motivation. So this is using pupil dilation instead of using measures of skin conductance or heart rate to measure autonomic nervous system activity. And in this case, what one would be measuring are so-called state-evoked pupillary responses. So not phasic immediate changes, but tonic changes across time as a consequence of specific events. So I think it's fair to say that there are two seminal papers that started all of this. And I wanted to at least give some credit here to the seminal leverage that these two studies have had. So the first one is by Ian Jackson and Sylvain Sirois, where they've really introduced this measure to the developmental community. So this is studying physical cognition using a factorial design, where they've really laid the groundwork for providing luminance control analyses, introduced a new way of analyzing these continuous measures, and really made a bold statement that they thought, and from a recent paper, I take it that they still assume and defend the idea that pupil dilation measures in these paradigms are a better and more sensitive measure than the traditional measure of looking time. So I won't walk you through all the details in the graphic here. I think if you haven't come across this paper, then the reference is provided at the bottom here. But I think this really introduced the field to this idea of studying physical cognition in young children. And the second seminal paper by Gustaf Gredebäck and Annika Melinda really then scaled this up by introducing pupil dilation into a paradigm where you can present video images, animated images, and then pinpoint in these live dynamic videos what it is or which events resulted in greater pupil dilation across age groups, right? So this moved the measure into the realm of social cognition and embedded the measure in not just a factorial violation of expectation paradigm, but into an experimental paradigm where you had, as it were, a control condition of rational events, so feeding in a normal way, and non-rational events feeding in a strange way, and then determining whether this is being registered by participants in terms of greater pupil dilation. And I think what really makes this research stand out is that the authors and also following research has really highlighted this benefit of using pupil dilation measures to index individual differences in socio-cognitive development. And as a sort of illustration of the third block, so it is also possible to measure pupil dilation in more live paradigms. So this is a setup where we measure children's live pupil dilation in response to a scene that they saw or watched through this magic window. So this is us taking a tonic measure of arousal, and then children basically viewing a person on the other side needing help and having an opportunity to respond to this and to help the individual. So I just want to briefly start this video just to show you that what we are trying to do here is to have children be active participants in this study. And you can see the live gaze, I hope you can see it on your screen, being taken as we take this continuous measurement. And you can see the live gaze tracking my colleague Katarina here, who's pretending to be clumsy and dropping some cloth pegs. And not only are we interested in seeing whether children's attention is shifted toward these cloth pegs, but as you can see from the child's movement, this is also about us finding out whether they would be motivated to help Katarina, and if they do so after they've helped or after somebody else helps instead of them, does this in any way affect their arousal? Right. So in this case, my other colleague Julian is a bit quicker than the child to help. So we've used this manipulation to find out in these before and after effects what it is that gets children interested and excited in a particular situation. And so moving this measure into a realm of motivation to be studied in experimental designs, where what we're interested in was whether children's own behavior has an influence on their physiological arousal. Okay. And then finally, the sort of last 3 points. So Krüger and colleagues have published this wonderful paper a couple of years back, and in their title, they refer to illuminating the dark ages. And I think it's a very fitting title because across a broad age range, as you can see in this graph, the authors just pointed out how helpful it is to have the same measure being used in different age groups to really get a sense of continuity. And any one of you who has a 2-year-old at home or who has been or is around 2-year-olds more frequently can attest to the fact that 2-year-olds probably hate few things more than sitting still in an experimental study. So this is really just to emphasize the utility of this measure to study a broad age range. And then finally, maybe a critical point that yes, it's easy to capture pupil size if you've got an eye tracker around, but please don't be tempted into thinking that this automatically means that you can collect meaningful pupil size data. So there is no free lunch when it comes to collecting pupil size data. And across the broad range of studies, there's currently no consistent way in which we should process these data. There's also no uniform way in which we should report or correct voluminance artifacts. In addition to samples being generally small in developmental psychology. So we do have some way to go. And what I've plotted here is just a graph answering the classic question of, well, how long should I keep my time interval? When do these effects start to emerge? This is from 0 to a few seconds after stimulus, just showing you for individual differences, studies, and experimental studies, what the sort of most frequently chosen time windows are in which colleagues study this phenomenon. So there's by no means, this is an evolving situation. I just wanted to point out that many of these things are still a matter of conversation. And just to point out here, there's also even further down the road, techniques in which colleagues have studied pupil dilation without an actual eye tracker. So just pointing to put up the reference here, this is very recent work. So developmental psychologists are really still exploring the boundaries of pupillometry. And so as a final slide, I do want to emphasize that psychologically modulated pupil dilation is a real phenomenon. And this is not just my opinion, this is based on these 93 studies comprising close to 5,700 participants from as young as 3 months to 16 years. And studying, and I've just illustrated this here in my second futile word art attempt on the right-hand side, studying many different psychological processes and having, as far as I could count, identified 25 different psychological mechanisms, as it were. And so I think a question for the future would be whether there are actually, these different mechanisms are actually part of a more global or general psychological mechanism. So I will end on just pointing out that, as you can see, studies are being published as we go. This is a evolving situation, it is a quickly developing situation. And I do continue to think that this is a fascinating method to use. And I would encourage everyone to try this out. And if you ever have any questions, either right now or in the future, if I can be of any assistance to share some of my fascination for this method, then please never hesitate to reach out to me. Thank you very much.
Excellent. Thank you, Robert, for this great presentation. I think I was exposed about 10 years ago to the topic of pupillometry and always found it very fascinating. I think you gave a really good introduction to the topic, like also exposing others to the topic from the very beginning, explaining what it's all about, and making sure that everyone understands its importance, but also the tricky parts. Because as you said, someone could say, yeah, well, actually, the data comes for free, so of course we can use it, but it's unfortunately not that simple. But also I haven't seen it yet, so I was super happy to see here the graph on the last slide that the number of presentations is increasing over time, because I know that a lot of researchers thought about using pupillometry in the past, but then as you said, it's not that simple to use. And then seeing the number of publications really, I would say, going through the roof over the past few years is really astonishing to see, and I think will give more insights and also will inspire more researchers using them in the future. Sorry. Maybe just to point out here, so you always have the option to give questions in the chat. So please do that as you see fit. Yeah, also some feedback here in the questions section saying, yeah, fantastic presentation, and yeah, looking forward to the meta-analysis chapter on the 93 studies you have reviewed, and really excellent. Thank you for the great summary. So yeah, I think really good to have it also in a format like that. Because you also showed a graph for the different ages, and then you could see, you mentioned then like 2-year-olds are really difficult, but then you could see that the curve increases by age, but then also drops towards the end. Would you have any explanation for that? Or like, what do you think would mean that, like, let's say, well, of course, adults, but then you could also differentiate maybe retirees, for instance, also it might look different. But yeah, how that, what that could mean essentially for future studies. So like, what age group would be of particular interest to investigate further?
I think it's a great question. And I think one has to give credit to this research team here, who were really the first to study this and to publish this on across such a broad age range. And the authors do provide a very extensive discussion of their age effect, but they're also very conscious, as I would be, of this being the first study of its kind. And I'm not sure whether we can read a lot into this sort of seemingly upside down U-shaped pattern here, which could be a consequence, as also the authors discuss, of the particular maybe simplicity of the stimuli, or maybe that it doesn't require an adult a lot of cognitive effort to be sensitive to a cow mewing or a cat barking, for example. So at this point, we don't know. I would take this slide to set a slightly different focus, which is you can use this method, the same measures, same processing pipelines across a broad age range. So the same stimulus can be presented to a 1-year-old and to an adult, and you can still get meaningful data from them. So I think this should be a starting point of more work to come that uses multiple age groups.
Yeah, exactly. Because sometimes some things are very difficult to compare for the different age groups. But then I think that's really something where you could say that's valid for everyone. We have one more, I think, time for one more question from the chat, which I think is also very interesting, because you mentioned autism in one of your slides. Could you please explain what the assumed connection between pupil dilation and autism is?
That is an excellent question, and I'm not trying to be evasive here, but this is quite difficult to answer in a few minutes. Because there are many studies which have used this measure with participants from an autism group compared to a control group, and I'm really not the person, the expert in summarizing this work. But from my reading of the literature and having worked together with a colleague who is an autism researcher expert, pupil dilation is generally used as an involuntary measure of emotional reactivity. And I hope that that's not too vague to answer this question. So it's used in the context of whether certain stimuli, such as, for example, emotional images, result in different emotional reactivities in children with autism and those and control participants. And if I had to ballpark it, there's close to 20 studies of these 93 that have actually been carried out in this context. And they are mostly interested in differences in both sort of tonic reactivities, so are there different tonic levels of pupil size between children with autism and control conditions, as well as differences in how both groups respond to emotionally charged stimuli. I'm sorry, I know that's not very helpful now. And I can't see the question, but by all means, feel free to write me an email. I'd be happy to send you the appropriate references. But I do want to make the point that this is a very active part of research, and there's several studies published on this topic, and they're taking different angles, which makes it a bit difficult for me to summarize it in this brief amount of time.
Yeah, absolutely. And I think everyone understands that you can only give a glimpse of the research that has been done and summarize it and then if someone is interested, it can start from here. So yeah, please make sure to reach out to Robert if you want to know more. So thanks a million. Now I would like to welcome Julian on stage to talk a bit about his research. Julian is a professor for clinical child and adolescent psychology at the University of Leipzig and head of the university psychotherapy outpatient clinic for children and adolescents. And we talked a lot about child psychology and also clinical psychology a lot in the past. And therefore, I'm super happy now to welcome him here on stage to talk about his studies that he's conducted so far in the past. So the stage is yours.
The introduction, and thank you, Robert, for being here. We worked together for quite a while in Leipzig at the Leipzig Research Center, and that brought forward my understanding of eye tracking and pupillometry. And I was one of the researchers who thought pupillometry would come for free lunch until I met Robert and I understood how difficult research designs and analysis are for this measure. And I was lucky to meet Robert, and we finally published one of the first papers on pupillometry data in children with anxiety disorders. And that's also a good point to mention that collaboration and collaborating with subdisciplines in psychology, such as developmental psychology or general psychology, I think it's very important to inform also applied research as we do it. And I'm happy that I can give you some insights how we try to use eye tracking technology to understand mental disorders and in specific anxiety disorders in children and adolescents. And I'd like to present two studies that we recently conducted. And as I said before, we focus a lot on anxiety disorders in children. Why do we do that? Anxiety disorders are among the most prevalent, most common mental disorders in children. Here we focus on social anxiety disorder. That means we have children, like you see here on the picture, that are afraid of both social interactions and social performance situations, such as giving a presentation or being evaluated by others. But these children are also afraid meeting unknown people, meeting strangers, coming into new groups like a sports club where they don't know anybody. And they are so afraid that both their academic and their social development in life is significantly impaired, and they have a lot of distress in their everyday life, both in their free time and their academic school time. We know that this anxiety disorder is very prevalent, so it's very common in children, adolescents, and in adults. And what's interesting, we know that most adults that have a social anxiety disorder, which is characterized by a fear of negative evaluation and particularly being in the center of attention by others, always having or being afraid that others might not like the person, that they might embarrass themselves, that these disorders start in most cases, almost 90% of the cases start during childhood and youth. Very interesting question is what happens in that developmental period that kind of makes children that anxious. And what's interesting that we have quite detailed models that propose that social fears are particularly maintained and caused by distortions in cognitive processes. These cognitive processes are very complex. They comprise both ruminative processes, lack of social skills, distorted self schemas, but also a big point or big part of these etiological models and maintenance models relate to distortions or distorted attentional processes, and that is why we try to study these processes to understand how they are affected in children with anxiety disorders, to understand how fear is maintained, and also to understand if attentional processes is a target for psychotherapy interventions, and also probably a measure in which you can measure treatment effectiveness. When it comes to attentional processes in children with anxiety disorders, that is an assumption that is also valid for other anxiety disorders, such as, for example, spider phobia or separation anxiety disorder. It is assumed that individuals with clinical anxieties have a hypervigilance avoidance pattern of attention. To illustrate that to you, you can see here this group of children, all looking quite friendly, but there is this one child who seems to be distracted or probably not interested in the interaction with the first person. And what the hypervigilance avoidance hypothesis assumes is that a child with an anxiety disorder, in particular with social anxiety disorder, who is afraid that others might be disinterested and might not like his or her presentation, or the child, him or herself, is very, very sensitive to any potential sign of social threat. And that means that according to this hypothesis, the visual attention and the first fixation would be very quick to particularly this child that might signal social disinterest. So we would have a very quick attentional shift to this person. And then in the following, because it is so negatively perceived, in the following we see an avoidance in particular of this social negative stimuli, because it is so unpleasant. And why is that problematic? It is problematic because this would lead to an overrepresentation of social threatening information, because so much attention is paid to negative parts of social information. And also what's assumed in these models, that this distortion in attentional processes will also lead to impaired social skills, because people with social anxiety disorders will particularly avoid eye contact and the eye region of others. And this, on the other side, will lead to the interaction partners thinking, oh, the child that is avoiding eye contact is less interested or probably bored by the conversation, which then leads to more likely social rejection. So here you can see that this hypervigilance avoidance pattern might play a significant role in the maintenance of the anxieties in children. I'd like to present some data that we collected. It was a larger research project funded by the German Research Association that we conducted at Freiburg University. We recruited children between the ages of 10 and 13 years old through newspapers, but also through schools. We had 3 groups. We had a group of children that were suffering from social anxiety disorder. We had a group of children with other mixed anxiety disorders, such as specific phobia, meaning a spider phobia or dog phobia, separation anxiety disorder, to have a comparison whether the findings that we have also regarding visual attention, whether they are very specific to this social anxiety disorder, or if they are transdiagnostic relevant phenomena that we also find in other anxiety disorders. You can see here on the right-hand side, on our diagnostic procedure, all children went through an intensive diagnostic interview with the children and the parents to make sure they met diagnostic criteria for an anxiety disorder, and also to rule out that they had significant other diagnoses that would influence attentional processes. Here you see the research design that we did. We had a 20-second free viewing task, the classical emotional face task, where participants watch or presented with emotional faces. We had 3 emotions. There was happy, neutral, and angry faces, and we particularly focused on first fixation to the eye region and the duration of the first fixation, which are measures to capture early hypervigilance, and then to capture possible avoidance. We then looked at the overall dwell time to the eyes. I have a gaze pattern for 2 children. One was a healthy control. I'll show you that because I think that's quite impressive to see how attentional patterns might differ between clinical and non-clinical participants. So you see here the gaze pattern of the healthy control child. You see you have rather stable and long fixations right into the middle of the face. Not so many. Scan pass was quite consistent in the middle of the face. And now if you look at the right-hand side on the bottom, you'll see the scan pass pattern of a child with an anxiety disorder. And you see that is quite different to what you saw from the first child. We have much longer scan paths, we have much shorter fixations, they are more distributed over the entire face, and have a sign of hyperscanning going on, which we did not assess in the study that or the data that I present to you now. So the data, as I told you, we looked at the first fixation, entry time into area of interest. Area of interest, as you see on the left-hand side, was both eye regions, and latency of first fixation. I'll just show if I can. Here, what you see for the 3 emotional expressions of the faces. You see the yellow graph is children with social anxiety disorder. The blue one is the clinical control group, and a light green is children without any mental disorder, so the healthy control group. And what you can see here, that the first fixation to the eye region, we found differences here for angry and also for neutral, suggesting that we have to some extent faster fixation in both clinical groups to the eye region. So children of the clinical groups were faster in the entry time of the first fixation into the eye region, probably suggesting hypervigilance to that part of the face. What is interesting, we found in our sample no difference between the 2 clinical groups, even though you see here that we have a pattern where the mixed anxiety disorder group is sometimes in the middle between social anxiety children and healthy controls, but the sample was probably not large enough. We are right now collecting much more data in a bigger project to see if we have a power issue. But you could say at this power level, and we had about 100 participants, we see no big differences between the 2 clinical groups, suggesting that the processes that we capture here are probably also have some transdiagnostic quality. What's interesting further, that we have duration differences between the social anxiety group and the healthy controls. Again, mixed anxiety disorders are in the middle. That we have a shorter fixation duration of the first fixation. So we have a very quick shift to the eye region, and then we have a shift away from that. So this could suggest that we have a hypervigilance pattern for the eye region in children with anxiety disorders. Regarding the dwell time, so that is the overall dwell time across the 20-second presentation interval. And you see here that we found pretty much no big difference when we looked at the entire 20-second interval between the groups. There was just a simple difference in happy faces, where we had less dwell time to the eyes in the mixed anxiety disorder group, but cannot really make anything out of that. But what's interesting, we looked more into detail and did a split in the sample, and we looked at male and female participants. And that is interesting because we know that we have differences in anxiety disorder symptoms between girls and boys, meaning that usually girls are much more vulnerable to anxiety disorders. They have higher prevalence rates. And what's interesting, that females, when we see them in our outpatient clinics, are usually much more impaired by the anxiety. So you could say they are sicker than the boys. And that's interesting because we found no differences in dwell time over the course of the 20-second interval. But what we found is that there is a separation in dwell time in females after 10 seconds or in the last interval of presentation. And it is that we see that healthy females kind of manage to look more into the eye region with longer presentation times, while we have more avoidance of both clinical female groups. And that could probably give us an idea that there are differential attentional processes at work, or that females might show differences in their attentional processes when compared to males. And that's also something we are following up right now in our study that we're doing right now. Yeah, we as I said, we used a laboratory classic paradigm where you had these still faces, fixed images, standardized facial pictures. And that's a paradigm that's used widely, and it's probably the most used paradigm in research. And that provides many advantages, that you have high internal validity, you have a high standardization, but of course it comes also with a lot of limitations, especially if you want to kind of draw conclusions about real life or real existing differences in attentional processes, because faces and facial expressions, as you see here in the picture on the bottom, where you have the teacher standing in front of the class. Of course, faces and facial expressions are not static in real world. But the problem is, if you assess gaze patterns in real life, you have also other problems, methodological problems. But if you use static faces, you have a low ecological validity. And as I said before, these studies that we do in the laboratory are probably very artificial and may not give us a good insight whether attentional processes are similarly disrupted in real life. So what we just recently did and finished, the study is submitted. It's a study done by PhD students of my working group, Leonid Liedl. We tried to use mobile eye tracking glasses during social stress, and we also we try to investigate attentional processes during a real life social stress test. Performance situation. We had a social stress test that consisted out of 4 minutes being in front of 2 unknown observers, answering questions about a story, an unknown story that the children listened to, and then they were given standardized questions regarding that task by the 2 observers that maintained a friendly but mostly neutral feedback appearance. And what we were interested in was whether children with social anxiety disorder would differ in terms of fixations to the face region, dwell time to the face region. And we also were interested in self-rating of eye contact, because it has been shown that children with anxiety disorders are particularly have a bias regarding their own performance, meaning that they usually underestimate their performance. And we wanted to see whether that relates also to their gaze performance, whether they judge themselves worse than they actually performed. And what's interesting, we did that stress test twice. So it was a stress test children did 2 times in a row with a small break, because we wanted to see whether a shift in state anxiety would relate to a shift in attentional patterns, because it has been shown that children with anxiety disorders show, particularly in laboratory studies, disruptions in their gaze patterns when they have high states of alertness, because that kind of activates their anxiety-specific, disorder-specific pattern of visual processing. So yeah, that's what we did. You could ask, why did you look at the face region and not at the eye region? At that point of time, the eye tracking technology was not, you could say, the resolution was not good enough to differentiate between different parts of the face. So we choose to focus on the face region as a whole. So what did we find? Here you can see the 2 tasks. There's the task that children did in the first place, and then after a break, a similar task again. And you have here in light gray children with social anxiety disorder and the healthy control children with the black graphs. And what you see is that we find no significant difference in task number 1. So there was a similar amount of fixations to the face region in both groups, but we see an improvement or a significant trend for improvement in healthy control children, meaning that when healthy control children did the task for a second time, they showed more fixations to the face of the observer. You could say they were more self-confident, or showed more self-confident and socially appropriate behavior. Similar pattern is shown when we look at the dwell time of the face. Here we see again that in task number 1, where state anxiety, and I'm going to show you the graph in the following, was quite high in both groups. Children, healthy control children and social anxious children did not differ, but in the second task we see more dwell time to the face of the observers. What's interesting, we asked the children how much or how much time did you spend on the eye region, or how often did you look into the eye region of the observer? And what we see that we see also an increase in the second task. And what's interesting, that we see children of the social anxiety group rate themselves for both tasks lower than the healthy control children, and that gives us a hint. And that's also when we run a regression analysis, we see that the self-ratings relate pretty well in our clinical group to the amount of fixations and dwell time that we measure with the eye tracking glasses, that we have a lot of variance that relates in the self-ratings to the objective measures, meaning that obviously children with social anxiety disorders in their ratings here are quite accurate to their real performance. And what's also interesting, we see that subjective anxiety decreases in both groups. In task number 1, also healthy control children showed quite high levels of state anxiety, because it is a challenging task, but then a very strong drop in both groups. Second task was less, elicit much less anxiety in both groups. And also when we run regression analysis, we see that this drop in state anxiety explains improvements in gaze measures. So we see that differences or improvements in fixation count and in dwell time is related to a drop in subjective anxiety in healthy controls, but not in the clinical group. And that gives us an interesting insight that the gaze pattern in children with social anxiety disorder is not that related to state anxiety, but rather something that is stable in, you could say, every social interaction, while children without anxieties show a similar pattern when they're pretty nervous, and when they overcome their anxiety, their gaze behavior normalizes. So as a summary, we can say that we find some evidence, and there are not many studies out there, not many research groups using eye tracking technology right now, but we see that it is becoming more and more popular, but we believe that it's a very important and interesting technique that allows us to capture aspects of psychopathology that we cannot measure by simple observation or other techniques. So we find evidence for both hypervigilance and avoidance in childhood social anxiety. And we see that eye tracking technology can teach us a lot of psychopathology, both in laboratory settings and in real life settings. And for us, it was one of the first studies that we conducted using eye tracking glasses, and we were quite relieved that the results were meaningful, even though we suffered from a lot of hassles while using eye tracking glasses when they moved and so on. I can tell you stories, but in the end we were quite satisfied with the data quality, and that's a good news, I think. But overall we need much more research, and also that should lead to developmental model of social anxiety and anxiety disorders in children to improve also psychotherapy treatments. Right now we see that when children with anxiety disorders go into psychotherapy, about 65 to 66% of children see a remission of anxiety symptoms below the clinical level, but on the other hand, we see that about 1/3 of children with anxiety disorders right now do not benefit enough from our treatment. So there is a lot to do to improve our treatment effectiveness, and I believe that studies understanding mechanisms of psychopathology are of great importance to improve our treatments. Thank you very much, and I'm happy to take your questions.
Thanks a million. The feedback that we've got so far is very positive, so very interesting talk, Julian. Thanks a million for that. And I think it really shows, like you said, a few studies have been conducted already, but much more needs to be done to really get a better understanding how it can be used as a diagnostic possibly, but also how that could also influence future therapy sessions, which then of course is also crucial. We have one question here in the chat to you, which is assessing social anxiety disorders in children must be highly dependent on the experimental method. For instance, could conducting a study online instead of being physically in the lab have an effect on the results?
Yeah, totally. I mean, our diagnostic that we do is the diagnostic interview that we do with children and with the parents to be sure that children meet diagnostic criteria. That's similar to what we do in our outpatient clinic, but of course, and that's what we see in our other studies, that children are highly anxious when they come to our laboratory, and it's a new surrounding. They don't know the experimenter, and we have also done some research where we, for example, assessed psychophysiology, and that's something we did at children's homes. So we also try to capture some processes when going to children's homes where they felt more comfort. But yeah, online studies have many benefits. Probably children are less anxious, state anxiety, but on the other hand, then you have less control about what's happening while they do it. So I think it makes sense to assess these processes in different settings.
Yeah.
But of
course, like always, it has benefits, but it also has some shortcomings there.
Yeah.
I think what you also pointed out, what I think is worth mentioning again is, because we hear that very often, that people come to us saying, yeah, we just want to conduct a study with the glasses, and we know eye tracking very well, so it's nothing new, so we expect kind of it will run as smooth as the other studies we did with the screen-based systems. And you pointed out that this is not the case. So I think it's worth mentioning that people need to have that in mind when they start a study, even though they have a lot of experience like you do with the methodology itself, but then doing it with kind of free-moving subjects, especially kids, I think it's even more so. It's a different kind of study then, different kind of methodology, and yeah, I'm really looking forward to see more results on that end as well, with kids moving around, seeing the social interaction, wearing the glasses.
Yeah, a big issue is the mapping of the fixations, because then you have movements of the glasses and then the fixation, like in our research design, is just a glimpse beside your area of interest, and you say, well, do I count that in? I know the glasses moved a little, and yeah, you have just also what you can't measure, and that's, I think, something you need to keep in mind is really scan paths. You can basically just measure fixations and dwell time, but not scan path length or anything.
Yeah, of course. Yeah, excellent. Thank you so much. In case you have any more questions also to Julian, please write them in the chat. I know we have a few questions that are not answered there, but we will keep them for later for the panel. And then I would like to welcome my colleague on stage, Marisa Biondi, who is Senior Researcher Scientist at Tobii Pro from North America.
Thank you. Thanks so much for inviting me. Good morning or good afternoon, depending on where you are today. I hope you're enjoying the symposium. It's been really great so far to see and hear about all this great research. I'm Marisa Biondi. I'm the Senior Research Scientist for Tobii Pro in the Americas. I'm really happy to be here and talk about our eye tracking solutions at Tobii and ways that you can use them to conduct research with infant and child populations. So I've been with Tobii now for a little over 5 years, but before I joined, I was a customer in research labs where we studied infant cognitive development. So I have a long history with Tobii, going on, I think, 14 years now. And it's really fun to be able to use my scientific background and support our research customers like you today. So a quick agenda, we're going to start with an introduction and a portfolio overview. You can see all the different options we have for eye trackers and how to set them up. And then I'll show you how quick and easy it is to set up a study in Tobii Pro Lab, which is our all-in-one software suite. And then we'll have the rest of the time for an interactive Q&A panel with my good colleague, Tobii Gredebäck, who is a product owner on our Tobii Pro Lab team. And throughout this today, as has already been mentioned, if you have questions, please add them to the Q&A function, and then we can address them when we get there. So our company started in 2001, and this was our very first eye tracker. We've been serving academic researchers with eye tracking ever since. I really like to show this first eye tracker because I feel like it shows and highlights how much innovation and change our company has seen in the last 20 years. Next, we have the Tobii 1750, which was released around 2005 and was very popularly used in developmental research labs. And then the X50 was one of our first portable systems. Some of these are still even in use today. But this is our current portfolio. And we want you to be able to conduct high quality, reliable research and be your research partner throughout the process. So we have a variety of hardware and software and enablers to get that done. We have these screen-based eye trackers, Tobii Pro Spectrum, Tobii Pro Fusion, and Tobii Pro Nano. We also have our wearable Tobii Pro Glasses 3. Our software is Tobii Pro Lab. We have some great partner solutions, which I'll highlight a little bit later. We do have an SDK and API, which are also free for use. So these are tools that you can use in your research that will deliver these reliable and high-quality results. So moving into the actual products themselves, this is the Tobii Pro Spectrum. It's designed to ensure high quality data and reproducibility. We have patented eye tracking algorithms, sophisticated hardware design, and hardware components. The Spectrum has a sampling rate up to 1200 Hertz, and it works for any kind of research, including microsaccades or EEG or other types of co-registration. It also comes in 300 and 600 Hertz models, and you can downsample even down to 60 Hertz. It is a dual camera system, so this allows the Spectrum to give you really high quality, complete gaze data stream for analysis. It has a very large head box as well to accommodate participant movement and flexibility in placement and participant management, as well as comfort for all your participants. No chin rest is needed with the Tobii Pro Spectrum. We have true stereoscopic eye distance measurement for locating the eyes of a free-moving user or child or even infant. The Tobii Pro Spectrum also has bright and dark pupil illumination, so we can test a wide variety of the population. It does have a built-in monitor that can be removed, and it even has a TTL in port for synchronizing data streams, and I'll talk a little bit more about that later too. But all in all, the Tobii Pro Spectrum is our best performing system for extensive research into human behavior and eye movements. Some of the options for collecting data with infants and children with the Tobii Pro Spectrum, you can use it with a built-in monitor, or you can also remove the monitor and use real-world stimuli, like here, this little puppet show, or even calibrate it to a larger monitor. The next in our hardware lineup is the Tobii Pro Fusion, which was launched in 2019. We really wanted a high-performing and portable solution with high accuracy and precision, also that flexibility when participants move around and when conditions change. So the Tobii Pro Fusion has sampling rate up to 250 Hertz. It also comes in a 120 Hertz model. It's also a 2-camera system with both bright and dark pupil tracking modes. The data processing all happens right there on board through our Tobii iChips, and it plugs in via a USB port. So it is really portable. It comes in a padded zippered case. Works with screens up to 24 inches, but you can also use it with larger screens on a tripod. And again, it's very lightweight and portable. You can fit it in a bag or a suitcase and carry it out into the lab or the field. So it works natively on existing desktop PCs, but it can also work with a laptop, or you can, like I mentioned, set it up with a tripod on another stimulus presentation, or use something stimuli in the real world. So it has testing, just like the Spectrum. You can use it both with a screen or without a screen with real world stimuli. Dr. Daniela Corbetta is one of our customers, and she discussed in a webinar the variety of ways that her lab has been using remote eye tracking in conjunction with goal-directed actions for infant populations between 2.5 and 24 months. There was no need for participants to wear any sort of wearable headgear or wearable eye trackers. For sedentary tasks like reaching, this is a really effective tool for good mapping between vision and action. So they really go into good detail in this webinar on how to set that up. So you can see here, this is the actual eye tracker, blends in with the background pretty well, and then obviously the hand is there for the baby to reach out to. So if you are interested in watching this webinar and learning a little bit more on how to set up one of our eye trackers and hearing from someone who's done it effectively, you can go to our on-demand webinar page, actually where you found this webinar, or type in Tobii Pro on-demand webinars in the search engine, and you can find it. It's called Eye Tracking in Infant Goal-Directed Behaviors. Finally, in our hardware portfolio lineup, we have our Tobii Pro Glasses 3, which was launched in 2020. We have revolutionized the data capture by actually embedding the eye tracking cameras and IR illuminators right into the glasses of the lens. So they're very cool if you haven't seen them in person yet. There's also an accelerator, gyroscope, and a magnetometer, interchangeable nose pads, and a microphone. It does come in 50 and 100 Hertz options. There's 2 cameras per eye, and like I mentioned, they're embedded in those scratch-resistant Swiss lenses. There's a 106-degree field of view, and again, they're lightweight and portable. They come in a padded case. So these operational parts have also been more integrated as compared to our Tobii Pro Glasses 2 to allow them to fit under headwear or different kinds of applications that could require a helmet. And then you can use these with children, as has already been demonstrated. We have said that the eye tracking glasses work with kids age 5 and up. You could probably use them with younger kids with some slight modifications, like maybe adding some padding to the nose piece to make sure they sit appropriately on the child's face. We've had a cool video up on our website where you can watch what kids see while they're drawing art, and there's kids of different ages, so it's pretty cool to see what they're looking at, how that changes over time. So the glasses will work for a variety of active or interactive tasks, like our last presenter mentioned, where a screen-based tracker just won't work. So a screen-based tracker could be used in a non-standard configuration, but might not be a great choice if there's interaction like the picture on the left where these kids are putting something together. That might not be a great option with a screen-based tracker in a non-standard configuration because their arms would get in the way. So I'll show you actually how this has been used. I had a special shout out to my great colleague Mike Bartels and his son Finn for putting these videos together and sharing them with us. On the left, you'll see Finn putting together a Lego kit wearing our Tobii Pro Glasses 2, and he was 5 years old. And on the right, he's 12 years old doing the same kit wearing our Tobii Pro Glasses 3. So one thing that really struck me was how in the younger age video, he had slower eye movements. It seemed to have longer fixations and more looking at the instructions. And then in the video when he's 12, he's got faster eye movements. He's really kind of knows what he's searching for, as well as shorter fixations on the instruction booklet. So again, this is just one kid, 7 years apart and together at LEGO, but this is, I think, a great example of how you can use our wearable systems to capture some really interesting data. Our Tobii Pro Lab software is an all-in-one software suite. I'm going to go into more details here shortly, but we really want it to be possible for researchers to conduct high-quality research and get started quickly. So the most expensive eye tracker is really one that gets stuck in a box because it's too complicated to work with. We really don't want this to happen. So Tobii Pro Lab is easy to use, easy to set up, a drag and drop interface for images, videos, text, web, screen recording. We have advanced options. I'll show you more about that, and then an easy co-registration with other types of physiological data acquisition tools. Yeah, I'll get started on that in just a moment. And then our Tobii Pro Spectrum, as I mentioned, has TTL in capabilities, but you can synchronize anything with our Tobii Pro Lab software using the TTL out functionality, which is included at no extra cost. So you can send out TTL pulses at the onset of every stimulus to things like EEG, FNIRS, HR, and more. So we have partnerships with some of the companies listed here for a combined solution, which means that the data is recorded in Tobii Pro Lab and in the partner software. The events are synchronized between them. And then as you conduct the analysis of your eye tracking in Pro Lab, you export that data into the partner software and fully merge it together. So you can really get a full integration while retaining the high-end analysis tools of each respective software. 2 final points here. One way that we can demonstrate our commitment to being a research partner is through our funding support services. This means we assist you in the application process for research grants. If you want to know more or have questions, please feel free to check us out online at tobiipro.com/FSS or email us at fundingsupportservices@tobii.com. We can provide lots of things, letters of support, one-on-one scientific consultation, review or edits of your grants, potential loans of your hardware, and more. So please feel free to reach out. I'm one of the people who runs funding support in North America, and I'm happy to answer any of your questions. If you have a grant idea that you just want to talk about, or if you're in the final stages of a grant submission that's coming up soon, let us be your research partner and help you through the process. It is totally free. We just want to help you be successful in your grant acquisition, and we can support you in the eye tracking products later on. And finally, Tobii Pro Connect is where you can go to access customer support, but you can also find great downloads, training materials, FAQs, and get in touch with our support team worldwide. And Tobii Pro Academy is our new e-learning portal we released for customers where you can learn about eye tracking. You have self-paced courses that teach you how to set up your system. So this will be great to, after today, where I give you a quick preview about Tobii Pro Lab. But if you want to dive into more details, you can go to Tobii Pro Academy. Both of these things are also free. So you can go to connect.tobiipro.com or academy.tobiipro.com. So now let's learn a little bit more about Tobii Pro Lab. I am just going to switch. Okay, I hope that everyone can see the Tobii Pro Lab interface now. This is Tobii Pro Lab. This is the main project page, and I really wanted to show this more because many of you may think that implementing eye tracking in research is a daunting endeavor, but I want to show you how fast and easy it is to use Pro Lab to get started. I'm going to be going through this pretty quickly, but we'll have, there are lots of more details, as I mentioned, online on Tobii Pro Academy, as well as some great webinars. We'll go deeper into how to set up and all the details of Pro Lab. But Tobii Pro Lab will support your research workflow from start to finish, study design, calibration, recording, qualitative and quantitative analysis without other tools needed. It's flexible to a variety of testing situations, compatible with all of our hardware, and then it also enables free head movement and comfortable experience for all of your participants with quality data you can trust. So as I mentioned earlier, Tobii Pro Lab is an all-in-one software package for every project type. including all the hardware I already showed you today. So for a screen-based project type, where you're presenting stimuli on a computer monitor. If you're using the built-in monitor for the Spectrum, or if you're presenting on a PC or a laptop with the Fusion, you will use the screen-based project type. For our Glasses 2 or 3 recordings, you'll use the Glasses project type. If you are wanting to do a non-standard configuration like we saw with the eye tracker, either without a monitor or used on a tripod with real-world stimuli, you'll use the scene camera project type. And this is what you'll set up. You actually will need a scene camera to record the video of the real objects. And then the external presenter mode is if you're using something like E' as a stimulus presenter. Tobii Pro Lab will co-acquire that stimuli, so E' will drive it, Tobii Pro Lab will record it, and then you can use all of our full complement of analysis tools for easy analysis. So I have a project already open, and I'm going to guide you through the steps. So I was actually able to collect some data with a baby I know. It's a friend's baby. We collected a recording last year. I wanted to see how well the data would work with the Tobii Pro Nano. So I have a recording from last year when she was 9 months old, and then a recording from about a week ago when she was 18 months old. So you can see both of them, and we can compare across the different time frames. So this is the project overview page. On the top, you'll see all the different steps that we go through: design, record, and analyze. If you only have Glasses and you have a Glasses project, you'll see only analyze. You obviously won't be designing or recording anything because all that happens separately. But for a screen-based project type, which we have here, you see all three. These are all the list of recordings that you have. It shows the duration of the recording, the date. It also shows the percentage of gaze samples found. And I think this is important to point out because I did use a Tobii Pro Nano hardware, which is a single camera system. And if I was actually collecting data for a project, I would have wanted to use something like a Fusion or a Spectrum, especially with a baby that's very active and moving around. So you'll see that the percentage of gaze samples is pretty low. You can use this if you're trying to consider excluding participants or recordings from a final sample, but it's also just good to see what amount of time the participant was attending to the screen. You can open up participant variables and add these things in. So if you've got gender and age, you might be able to even add things like scores from other metrics. For example, if I wanted to add in a Bailey scale score or percentile, I can do so just by clicking this little plus button here. And then you can add in all the different variables. Participants is where you'll see all the different participants. You can change their names, you can change the different participant variables as needed, and then add more participants if you need. I'll close some of these. The events are where you can create and code custom events in the timeline. For example, if you wanted to code when they picked up a toy, if that was part of the testing scenario, you could code that, or if there was something like a verbal response. You can create those here just by pressing the plus button and give it a name, and then it has a shortcut to make it easy to log in the recording. And then finally, stimulus variables are where you can add different elements of the task, like if a task was easy or difficult, or if there was a target present or a target absent, just by clicking the plus button. So now we'll move over to the Design tab, and this is where you can create different timelines to present with your stimuli. It's so easy to add stimuli. You can either drag and drop or click and navigate to the folder where the stimuli are. Click and add, and it's already there. So in this case, it's a little bit small. I'll click Fit to Screen, and we're ready to go. It really is this simple. So the first thing you'll see is that a calibration card is always present. You can click and choose the features. For infants and children, you might want to use something like a video and the manual calibration type, or especially for infants or even non-human primates, this resizing video is a fairly new feature that we added. So it will have a nice big video, and this is one that we provide with the software. The video is great and interesting. It's a caterpillar moving around, and as the calibration points, as the infant's going to look at the different points, it will shrink to the certain corner where the calibration target should be, and then expand again. So keeping their attention moving with this really interesting video. It's a great feature. There's also a really nice video on our website, on our webinar hub, that goes into more detail about this infant calibration feature, so you can check it out. So Adding different stimulus events is super easy. You can also add group elements. So if you wanted to have a way to randomly select or present some different elements, you can add that in. It's just the group folder feature right here. You can add in images or videos. You can also use web stimuli. Obviously, you wouldn't use that for, probably not for infants, but that is a feature as well. You can even do screen recording. To add a stimulus to a folder, click drag and drop, and then you can expand it, and there it is. By changing different features of the stimuli, this is very easy. I already showed you how to fit to the screen. You could change the name. You could also change the background color if you wanted it to be white, for instance, and not show the black on the background. You can also determine how you want the slide to advance. So you can advance on time. So the duration can be as minimum as 50 milliseconds. You can have the stimulus advance on gaze as well. So if you click gaze, then you can set how long you want the gaze to be before it moves on to the next one. And then when you click on the actual stimulus itself, you can set the gaze zone. So if you want it only to move forward on gaze if they look in this particular zone, you would move the area to cover that zone. Then we go back to timeline, everything's ready to go. You can also advance on key press or mouse click, so that will give you a little bit more control. So depending on your participants and your study type, you could do that. So you can either do time or gaze, you can select multiple or all of them as well. So a little bit more about the groups. We have different actions that you can take. We can show all of them either in a sequential or shuffled order. You can repeat this folder. So if you had 10 in there and you wanted them to be shown multiple times, or if you wanted this to be shown multiple times, you can select the number of repetitions. Or you can even set a sample. If you've got 50 images in here and you want to sample 10, you can select random with replacement or without and set the sample size for how many you want to be shown to each participant. So that way it'll show a truly random sample to each participant that watches that timeline. And then you can also set those stimulus variables right here at the bottom. So if I wanted to say this was an easy or a difficult task, you can set that very easily there. And you can use that later as you're visualizing your data in the metrics visualizations. It's also exported with the data. For the record tab, you have to ensure the eye tracker is selected. I don't have one set up today, but you can also use a mouse tracker if you want to test out the timeline for recording. It will actually follow along the mouse and pretend to be eyes and visual input. And then you just select the timeline to present, give a participant name, recording name, and start recording. So we'll move along to the analysis tab. The first thing I like to do is find the video recording and replay it. So I will show you that here. This was the original video. So I just wanted to do a quick test of the Nano to see how it worked with a 9-month-old baby. It worked okay. And then I had a photo of some cats that we were fostering at the time. So the red dot here is where this baby was looking. And I'm just going to click through to show you different fixation points. She did like looking at the cats and meeting the cats in real life too. You can see how well it's actually doing fairly well, accuracy and precision wise. She's looking at the cat's eyes and ears. So this is the fixated data, but you can also look at the raw data as well. If you wanted to, during this time is where you could code events. So if I wanted to code something like picked up a toy, I could find that particular part in the video and click either the shortcut or click the little log button there, and it would log that event. Cool. Okay. I will move along to the other qualitative review. So for qualitative analytics, we have aggregated heat maps as well as gaze plots. So these all come up instantly. It aggregates across all of the recordings. You can even choose if there are certain ones that you want to be included or not included. In this case, I'll highlight all of them because there's only a couple. So this is what a gaze plot looks like. You can right click and save this to a file. sorry, a heat map. This is a heat map. This is a gaze plot. This is 2 of the recordings from this baby Sophia. Both of them are her, but one is blue and one is red. So you can see where she was looking. She was primarily looking at this diagram of a face on this eye, and then this scrambled face, she was looking at different areas, but this one kind of looks like an eye and is in the same place. So again, these aggregated recordings will show you truly aggregated with the heat map, or gaze plots as individual recordings kind of side by side showing the order of fixations. And if you hover over, you can see what number it was in the fixation order. This is our AOI tool, so you can draw different shapes or sizes on static stimuli and give them names. It's very easy using these little tools to just draw a shape. You can delete it. You can even copy it and paste it on another stimulus to keep all your AOIs the same size. And that's what I've done here. I give this one a name normal, and this one is scrambled. And I even tagged them as normal and scrambled under there. So for example, if you wanted to link all your distractor stimuli or target stimuli together across AOIs together across the stimuli, you could do so to compare them later. Okay, for the quantitative results, the first thing we'll do is go to the metrics visualizations, which is a really cool tool to give you a quick overview of results and trends. You can look at different metrics like time to first fixation or total duration of fixations, and I've set that up for face type. So here you can see the normal face type versus the scrambled face type. This is the total duration of fixations that occurred, and this is the mean. So on average, as Sophia was looking at these faces, she looked longer at the normal upright face as compared to the scrambled face. And this is a really nice tool to show you quickly how your study is progressing without doing a lot of analysis outside of ProLab. You can get a sense of, is your study working? Are your conditions correct? Before you really get to the heavy metrics export. Okay, metrics selection and export. This is the last part. Once we get you to this part, we export the data, and then you are outside of ProLab in whatever is your favorite data analysis software. So metrics selection, we have a couple different types of exports. The Excel report just gives you kind of the overview and highlights of the different AOI fixation metrics, visit and clicks. So you do get things like fixation duration, how long did the participants look at a certain area, or latency to fixate, how long did it take them to look there. You get counts, how many fixations or how many visits to an AOI, so how many times did they look in AOI. You also have event metrics like the number of events or duration between events, mouse clicks in an AOI if you have any mouse input like latency and count. You do get saccades like amplitude, velocity, or saccade count. We have some specialty reading metrics, which are great, like regressions and rereading durations. And then pupil diameter is in the data export. So the Excel report, and we have a couple different other types of files here. And then the last thing is the data export, which I mentioned. This is all of the XY data for each eye and each sample for the entire recording. This is also where you'll find the pupil diameter estimates before you export that for your favorite software. So just to quickly show you what those look like, this is the metrics. I hope that you can see this here. The Excel metrics, and then we have the AOI-based metrics. So this would be really easy to import into an analysis software because it's set up as a grid. And then the data export with all of the X, Y, Z coordinates. And then I have highlighted here to show you the 2 rows for pupil diameter left and pupil diameter right, and you can see those changes over time, and you would use this also in an external software to analyze. So I hope that I showed you today how easy it is to set up a study very quickly in ProLab and get started with your research, and how you can have a variety of different metrics exports. If you have any questions about Tobii Pro Lab or any of our products, we're happy to answer those now. You can also feel free to reach out to us as well on a variety of platforms. If you have questions about any pricing, you can email sales@tobii.com. And I think I'm finished with this part, and we can take any questions if there are any. Yeah, thanks.
Great, thank you, Marisa. So we have some questions. I will just bring them up here.
Great, and if Tomas wants to join.
Actually. I think some you already answered, but it's anyway good to repeat it so that we make sure that they are clearly answered. So because one was about the Tobii Pro Fusion, if it is compatible with ePrime 3.0.
Yes, so actually the compatibility with ePrime is through Tobii Pro Lab, and Tobii Pro Lab is only compatible with ePrime 3.0. So if you're an ePrime 2.0 user, you would want to upgrade to 3.0, and Tobii Pro Lab and ePrime can actually be used all on one computer to present and co-acquire that data all in one place. So yes, it's all through Tobii Pro Lab.
Then are the eye-tracking glasses correcting for head movements, especially if I move my head but not my eyes?
Great question. So I didn't mention anything about the fixation filters. Tomas, is this something that you want to talk about a little bit, how you do the fixation filtering in ProLab?
Yes, so there's some level of head correction, but it's very little that we do. So most of the processing for the gaze filter is actually in the reference of the head. So if you really wanted to do pure head compensation using eye-tracking glasses, you will need probably to use more extensive algorithms than the ones we have today for fixation filtering, or use some sort of mapping tool. I think Julian mentioned something about that. So a mapping tool would allow you to map from the environment into like a static representation of that environment. And in that case, that allows you to compensate for any sorts of head movements. But in general, when you record with the glasses, you're within the reference system of the glasses. So the head movements are not compensated for. Other solutions that are also available are solutions where we use markers, and those are infrared markers together with a motion capture system. And in that case, we know the orientation of the head in space. We know where the eyes are looking in the reference to that, so we can compensate for their movements in those setups. But yes, there is, I guess, and I bet there is some research on the topic on how to actually compensate in gaze filtering for head movements. But it's not something that we're on top of at the moment, no. So to say.
I think it really also depends on what kind of activity your participants are engaging in. If it's something like sports, you probably really would want to have some more something like the Qualisys or Vicon system with the marker kit to understand where they are in space, versus just like a task with the Legos like we saw. That may not matter as much. You may not have as much influence of head movement on the eye movements. Yeah, great question.
Thank you. So one question is also, I just need to see because there are more coming in. Does Tobii Pro Lab also work with older Tobii tech, such as the X230?
Yes, ProLab works with all of our older products. I believe or most of our older products, as long as they're in the TX series. Is that right, Tomas?
Yeah, so the X230 will work with Tobii Pro Lab, yes. We have also like the older X series, not as old as you mentioned X50. X50 is a bit too old, and the T 15, was it 1750? These are older series that we don't support. But anything from the X2 series, X3 series, X60, X120, T60, T120, all those older models are working with Tobii Pro Lab, yes.
So then I would say a bit of, maybe not tricky question, but definitely a very interesting one is one of the issues that they are having is they try to figure out in how to integrate PsychoPi with Tobii Pro Lab. And the reason for moving in this direction is that they are hoping to better represent the temporal aspects of the stimuli. So they know that what information they want to send to the eye tracker from PsychoPi, but on that stage of learning how to implement it, does Tobii provide support on this?
That is a really good question. I've actually talked to the people at PsychoPy recently about trying to get a better understanding of how our products work together, but there is a toolbox. It's the TITA toolbox, T-I-T-T-A, and you can find that on GitHub, and it's a way to synchronize PsychoPy with Tobii Pro Lab. But in terms of support or supporting the customers, it's a little bit tricky. I'm not sure if we're quite there yet, but it's something that I'm glad that you brought up, and we can take a look at how to have better documentation or support through that. Tomaa, do you have any other comments on that? And
no, I think that's the right answer. Very much the TITA toolbox can help out. So it's TITA. You can find it on GitHub.
Yeah, but I also will flag this question so you can get in touch with Tina to check if there are more questions.
Okay, great.
So then there's a question regarding the key press function in the properties, if they can choose or see what the key pressed, which key is pressed by the participant.
Go ahead, Tomaa.
Yes, they can. So the right now in the design, you cannot choose exactly which key you want to select for moving to the next stimulus. It will be any key press, but when we record it, we record which key specifically was pressed. So you will see that in the recording, and it's associated with the event of the key being pressed. So you know at which time it happened and which key was pressed. Yes.
Okay, cool. Then another question about AOIs. So how would you do the metrics visualization for an AOI without creating a tag group? For example, if you have only one AOI, is that possible?
Maybe you want to take that one too, Tomaa. I did breeze through the metrics visualization pretty quickly. I think is there a webinar on our website too about that, where it goes into more details?
I'm not sure, but it depends what is the condition you're trying to visualize. If you have only one AOI, you could get some metric. For example, if you're trying to discriminate on or compare on participants, that's already one condition that you can use to create the metric visualizations, even though you only have one AOI. Then I guess it really depends exactly what conditions you're trying to compare there. But yeah, if you had only one AOI and no tag on it, or only one tag on it, maybe you're interested in the different behavior in different participant groups, then that's already one condition you can use to actually plot against in the metrics visualization, if that is what you're interested in, of course.
Yeah. Yeah, if you wanted to compare between different conditional groups, for instance, like pre-treatment or post-treatment, I only had one participant. It was the same baby, 2 different time points. So I guess I could have had time 1 and time 2. But yeah, that would be another way. But I'm pretty sure there is a webinar on our on-demand webinar hub that goes more into details on binning and metrics visualizations as well. So you can search that.
I think we have explained that previously, yes, in the webinar.
Yes, yeah. So that would be a great thing to check out if you have more questions about that feature.
So then another interesting question about measuring microsaccade and if that is possible. So this candidate believes that currently they are detected as saccades. However, in some cases, they do not necessarily reflect a shift in attention and should be considered as a different response.
Yes, so I mean, today with the way the fixation filter functions in ProLab, so the IVT fixation filter, it's very much meant to measure some level, some attention, basically. So you can always, of course, play with the settings a bit and lower that velocity threshold and maybe catch microsaccades there, but they will be classified as saccades anyway. So probably if you're looking into microsaccades specifically, you might probably want to consider using other filters to apply to the data rather than the IVT filter. So that would be probably the way of doing it. Yeah.
Yeah, thank you, Tomaa. We have a few more questions. So is there a possibility to output the real-time data so that we can see for each participant in the data file at which current real time he or she has been presented with a particular image?
I think the only way that you can see real-time data is through our SDK. Is that right, Thomas? You have any other ideas?
Or did I understand it differently, the question? Can you read it again, please, Peter?
Yeah. So the question is there a possibility to output the real time so that we can see for each participant in the data file at which current real time he or she has been presented with a particular image? But that sounds to me that this is like post-processing.
Yeah, so I think I understand it the same way as you do, Peter. I of course, when you do this data exports or matrix exports in ProLab, all that is considered or taken into consideration when we're calculating those. In the data exports, you will get specific events marked inside the recording. It's like you will get many rows corresponding to all the different samples you have, and some of those rows are going to represent events in the recording. And there will be events that will tell you, for example, a new image stimulus X has been presented and image stimulus X stopped being presented. So you will have those markers in the data, so you can afterwards, associate this chunk of data was for this specific stimulus, or that chunk was for that specific stimulus. Same way for the matrix exports. We have different levels of matrix export. There are matrix export where you get the specification of exactly which stimulus was being presented, which area of interest, and even like which, I would say, trial presentation of that specific stimulus it was. So you will see that in the data, yes.
Yeah, I did breeze through that pretty quickly, but that was the last Excel sheet that I showed was the data export of every single sample. And if anyone is interested, we do have a 30-day trial version of Tobii Pro Lab that you can download on our website. And we even have sample projects you can download with real data. So if you wanted to explore a little bit more in the exports, see if you can understand, or if this is going to be the kind of export that you're looking for in your data analysis, please feel free to do that. You can Google Tobii Pro Lab, download, and find all of that information.
Yeah, that's a very good point. So you can play around with it a bit more, even though you don't have a license at hand.
That's right.
So the next question is about a serial reaction time task with an 8-element array. Is there a good enough resolution with the Tobii Pro Spectrum to distinguish fixations to points on a 4-column and 2-row array? But that, I think, depends highly on the size of the columns and arrows, right?
Yes, mostly. So it will mostly depend on that. So anything below, say it this way, anything below 1 degree of visual angle can start to become difficult to detect from one another. But any stimulus that is designed with at least 1 degree of margin between the different areas will be, I think, good enough to be used with spectrum and really have a clear distinction between the different areas there in the data sets. So, and of course, it depends on the participants. I mean, if we're talking about 6 months old, or if we're talking about adults, it will be, of course, harder the younger the participants.
Right, that's a good point.
Yeah, we just got the response that she would space it to take up the whole screen, so that it's not just like a tiny table in the middle, but really take.
Oh yes, most likely yes. You use the screen space you have.
Yes.
Yeah, and with preschool to school age children, so yeah, I think that's a really good idea. We have one more question left, even though we are a bit short in time. Is it possible to combine text with automatical AOIs for words and picture or video in a single screen in Tobii Pro Lab?
So we do have some really great text features that are new as part of our reading metrics. So if you input text into the text feature, it will draw AOIs automatically around the character, word, or even sentence level. Tomas, do you want to share any more about that feature and then some of the other to answer this question?
Yeah. So I think the question also was very much about if we could have also like images and videos as well, right? So that's not available at the moment, but these are things that we're investigating. So we're willing to go more into that direction, but it's not yet available in the software.
Right, thank you, Marisa and Thomas, for presenting and answering a lot of questions. Now I would like to welcome on the virtual stage Susanne Enke, who is finishing up her PhD thesis at the moment, talking about her project.
Hello everyone, thank you very much for the invitation and the opportunity of presenting my research in today's webinar. I will present some data from 2 studies on cognitive differences between monolingual and bilingual children, which were both part of my dissertation project. And I will start by summing up some physiological basics that we already heard in Robert's presentation. And yeah, I was lucky enough to benefit from his expertise on eye tracking data and data preparation. And yes, so as we already heard, the pupillary muscles that are like the basics of pupil dilation and the differences in pupil diameter are not only influenced by brain systems that are involved in the pupillary light reflex, but also by brain systems that are involved in cognitive and autonomic functions. And the most important one is the locus coeruleus, or LC. And in the graph at the very top, you can see the connections of the locus coeruleus and the norepinephrine system, which is very important for those for this reactions of the pupil in the brain. And so you could say that pupillary changes are an important indicator or an indirect measure of brain activation, and they have been used for this since a lot of years now. And yeah, what is also important for my research is that the LC receives some efference from some brain regions, and amongst others, the anterior cingulate cortex, or ACC. And this brain region is also very important. Is one critical brain region that is related to both the bilingual language switching and the executive control network. And yeah, this will be like the link to my research and my research focus. What is the executive control network? Well, again, let's start with some basics. The concept of executive functions or executive control can be defined as top-down cognitive processes that are involved in the conscious and goal-directed control of thought, action, and emotion. They're related to the prefrontal cortex. And in bilingual and monolinguals, there have been sometimes found differences in this area of cognition in favor of the bilinguals. However, those differences have not been found consistently, so they depended largely on task characteristics and the age of the sample under study, for example. And so we were interested in my studies, under which circumstances do these differences emerge, and what could be underlying processes. So in the first study, we examined planning performance in bilingual children. Planning is a complex task that is also related to the executive functions and the executive control network. And so our aim was to understand, as I said, the underlying cognitive prerequisites in bilingual as compared with monolingual children in this planning task. And especially we examined 2 mechanisms that could possibly indicate those differences in processing, cognitive processing. The first was related to more behavioral results, behavioral data, the so-called self-regulatory speech. So you can use speech for regulatory purposes to regulate your behavior, to regulate your emotions. And this was like the first research interest, but today I will focus on our second one, which was the mental effort exhibited during task performance. And in adult participants, it has been shown that bilinguals might show a more efficient use of neural resources in tasks that are related to EF, so executive function. And we were wondering whether this could be related to bilingual children. And so we hypothesized that bilinguals might be able to solve those cognitively demanding tasks, like a planning task, while recruiting fewer neural resources than their monolingual peers. So yeah, this was our second research question. Would we examine, would we find less effort in a planning task, regardless of task performance? So it was really the process we were interested in, and this mental effort was measured via changes in pupil diameter. Here's some details on our sample. So we investigated primary school children of the 2nd to 4th grade. They were either monolingual German or bilingual German-Russian speaking. We limited our sample to this language group because we also investigated Russian language competencies. And here's some more details. I won't talk about everything in this slide, but you can see that we had like 30 children in each group. They were around 8 to 9 years of age on average. And yeah, we had also equal gender distributions. Okay, so the children solved a computerized so-called Tower of London task. This is a complex planning task, which you can see on the top of the screen. It is like a complex puzzle where the children have to manipulate some balls that are presented on pegs of different lengths. And so the children have to manipulate a start state into a goal state by using a computer mouse. And this task is preceded by some time to plan their moves and to have the opportunity to optimize their solution and to solve the task in the minimum number of moves possible. We coded one item as correctly solved when the children could, on the one hand, name the least moves necessary, the minimum number of moves, and also completed it in the minimum number of moves. And we had a slightly complicated experimental design. I will not explain all the details, but what is important for you that there were 3 experimental conditions. The children had either they had no additional task during planning. So this is the first condition here. It's a regular condition where they just planned their moves and did nothing besides this. Or they had to tap their foot every second. This was the so-called tapping control condition. Or in a third condition, they had to utter the word Monday every second. This complicated design was because of our first research interest that I shortly mentioned, the self-regulatory speech, and the 3 conditions were presented in randomized order. So here you can see how we presented the task on the screen, what the children saw. Each trial started with a baseline. Afterwards, they saw the start and the goal state of the Tower of London, could plan their moves. And when they had stated that they were done with planning, they were told, so how many steps do you think you need? The experimenter entered this number, and afterwards the children could manipulate the balls. And during this planning phase in the beginning, we measured the pupil dilation, the pupil diameter, and related it to the baseline that we recorded at the beginning of each trial. Here's some more details on the pupillometry. We implemented all task recordings and data recording using Open Sesame, an open source program. Distance to monitor was an average 60 centimeters, and with a sampling frequency of 120 hertz. We sampled the pupil diameter and the gaze with a Tobii unit that was positioned below the monitor. Each experimental phase was preceded by a 5-point calibration phase. And before calculating our baseline corrected measure, all data were filtered, interpolated, and averaged across the right and the left eyes. And now I will already present the results of our research question. So we conducted 3 linear regressions for each condition and predicted children's mental effort. We controlled for some variables, the language competencies, which differed between the 2 groups of children, the socioeconomic status, and also performance accuracy, because we were not interested in the performance behavior, but only in the effort. And this is a slightly huge table, but I will quickly walk you through this. So you can see in the first step we have our control variables, which I mentioned, socioeconomic status, language competencies, and planning accuracy. And the important bit here is that in the second step we added language group as a predictor. And as you can see, in all 3 conditions, so regular, tapping, and articulatory suppression, language group significantly improved the prediction. And yeah, especially in the more complicated conditions where the children had to solve an additional task, the bilinguals did this with significantly less effort than their monolingual peers. And I also brought some graphs where you can see this very good in detail. Here we have the 3 conditions: the regular condition, tapping control, and articulatory suppression, and all 3 conditions averaged for the 5 seconds after the start of the trial. The bilingual group was clearly below the monolinguals, especially in this most complicated condition where the children had to also utter a word while planning their moves. And what do we make of those results? We saw that there might be an advantage for bilinguals, which isn't reflected in performance always, but under some circumstances in the processes they use, so in recruiting of newer resources. And one next step would be to examine how are there certain circumstances where the bilinguals can also profit from the advantage or benefit from their advantage also in cognitive performance, or is it really just a reflection of differences in neural organization? And to conclude, you could say that there might be not a bilingual advantage, but a bilingual potential. And if you're interested in more details on this study, it has already been published recently in the Journal of Experimental Child Psychology. And I will now continue with a short insight in a second study. At the moment, we are preparing the manuscript. And as I said at the beginning, for both studies, our research interest was, are there certain circumstances when these advantages appear, and what are the processes that are underlying those advantages? And we were investigating this for another task, also of the executive function domain. And here are some more details that authors have distinguished between several types of executive functions. And classically, the so-called cold EF operate in emotionally neutral settings. So it's like the planning task you saw before, or other tasks include measurements of working memory, and it's fairly neutral, and there are no rewards being made, or it's not very significant for the children. But in so-called hot AF tasks, it operates in emotionally relevant situations, and those task performances are also associated with different brain regions, like the orbitofrontal cortex and other medial regions, which you can see on the graph in the top. And to date, very few studies have investigated performance on hot AF tasks in bilingual children, and this was what we were doing in this next study. And our question was, of course, so could we observe this less the less effort which we saw in the study before? Is it also does it extend to other tasks, and is it also apparent in different types of tasks, like those hot executive function tasks. And what we did was we administered the Iowa gambling task. And in this task, participants have to choose normally one out of 4 decks of cards to receive monetary gains. And with a certain probability, money or points are lost. And it is the task for the participants to extend their gains by learning to choose the most favorable options, so the 2 options that are more advantageous on average. And in our task version, children were told to help a fairy gather gems in order to rebuild the fairy's village that had been devastated by a thunderstorm. And those gems were hidden behind 4 doors. And the children were further instructed that sometimes elf children would hide behind those doors, playing a trick on the child and take away the gems. So the children had to click on one of those 4 doors, and afterwards the door would open, and it would reveal how many points or gems had been gained or lost. And as you can see here, in this example, the child chose door number 2, door B here, and it saw afterwards that it had gained or found 4 gems, and none of them had been lost. And yeah, this is what the children saw. They started again with the baseline. Afterwards, it's the stimulus where they had to choose one of the doors, and afterwards the feedback screen of 2000 milliseconds. And this task was presented in 2 conditions, in a standard and a reversed condition. I will in a second explain what this means. It was 5 blocks and 10 trials each, so in total 200 trials. And yeah, it was a fairly long task, long session for the children. As I said, 2 of the doors were advantageous, 2 were disadvantageous, and the children had to learn which were the better options. And this is I would just explain it for 1 door, so you can imagine how the task worked on the probability level. For the standard task, doors A to D differed in the amount of gems that could be gained or lost. So here you can see that for the doors A and B, in each trial, 4 gems were being gained, and for doors C and D, in each trial, 2 gems were being gained. And with a certain probability, an additional gems of 10 or 50 or 2 or 10 would be lost. And those probabilities and those amounts of gems resulted in a net value on average over the trials that were taken. So on average, the doors A and B would be disadvantageous and doors C and D advantageous. And also the probability of loss differed between the doors. And the children could not see this, and they had to learn it by memorizing those results and making the experience. In the reverse task, it was the same build-up, but on the standard situation was that gems were being lost, and in some cases gems were being gained with a certain probability. Okay. Again, we calculated the mental effort via changes in pupil diameter. It was again the relative change in pupil size in relation to a baseline. For this baseline, we took the first 100 milliseconds after the participants had selected a door. We excluded the first 1.5 seconds because of the light adaptation of the pupil. And that means that we were interested in the mental effort during this response integration. Pupil dilation was calculated over the 5 experimental blocks for each of the 4 doors I talked about, and also for both task versions separately. And what is also important, that for both of the task versions, we only included trials that resulted in either a loss for the standard task or in a gain of gems for the reverse task, because this was the situation where it deviated from the standard situation of the task, and we were interested in the effort children were exhibiting. And as I said, I'm already preparing the manuscript, so I will just present some first results for you. Again, there's a slightly huge table, but I highlighted the most important parts. I calculated multi-level models with blocks nested within individuals. And if you have some question on this, we can talk about it later. But the most important bit for you at the moment is that the language group was no significant predictor for our dependent measure, which was again the mental effort undertaken by the individuals. However, there were differences concerning the doors that had been chosen by the children. And again, I brought a graph for you where you can see it on some more detail. Here you can see we just calculated it for the last 500 milliseconds of this 2 seconds of presentation. And again, you can see that here the door B differed in comparison to the other doors. That was the most important finding. And when we go back to the overview of the choice options, you can see that door B was especially was special because it had a very huge loss or very huge gain, and this also happened with a probability of 10%. So what do we make of these results? First of all, we did not find a difference between the 2 language groups, but we found differences between the available options. And again, what Robert told us in the beginning, that there are a lot of possibilities to interpret those pupil data, and you can make a lot of it. And here you can see that maybe it could be another indicator instead of mental effort, or it could be an indicator of mental effort, but also of a learning process taking place. The anterior cingulate cortex, which I mentioned at the beginning, is also involved in conflict detection mechanisms. And these conflicts can also occur or operate as a teaching signal. And so you could see that maybe for this task, which is related to decision making, the children were just learning which doors would be more favorable or less favorable on average. In further analysis, I will look at the relations between the mental effort and the choice behavior, and maybe we could see that the mental effort also will predict the development of choice behavior over blocks. And to sum up, what we already heard today in those interesting talks was that pupil dilation is a very promising method for developmental research. It is a well-established method for the assessment of mental effort during execution of cognitive tasks. It is an objective measure for participants who are too young to make reliable self-assessments. And it is much more easily applicable in children than other neurophysiological methods. Okay, thank you very much for your attention, and thanks also to all the participating children and their families.
Thank you so much, Susanne, for the interesting study. And also what I really like to see, that Robert in the beginning talked about the methodology of pupillometry a lot, and you kind of showed what you can do with it in a really nice and interesting study.
Thank you.
What I'll ask myself is, because you looked at kids learning German or German and Russian, if you would believe that depending on the language that they are learning, because like German and Russian don't have so much in common, if that might differ, if you would say it would be, for instance, German and Dutch, or German and Danish or Swedish, which are more related, if that makes a difference, or if the other language maybe would even be more complex, like for instance Arabic, where they also read from the other side and so on, if that would have an impact on your findings. I think we lost your voice, so it seems you're on mute. Susanne, can you hear us? Because we can't hear you anymore.
Oh, sorry. Yeah, you weren't able to.
No, now it's good.
Yeah.
Now it's good.
Okay. Sorry. Where did it stop? What did you hear? Or did
We
you
didn't get anything. Like I was finishing my question, and then you started talking. What we saw, it's not working.
Yeah, I'm sorry. Okay, no, I just said that. Yeah, like the underlying rationale behind those results is that it does not matter which language we are talking, but just the fact of learning or speaking two languages, poses like an effort on your cognitive resources, and it kind of changes the neural basics. And so, but it would be interesting to see if you could extend this, of course, to other languages being spoken. But yeah, that would be the short answer.
Because that would lead to another question that we had in the chat. Is because if you would like to plan to follow these subjects further as they grow, potentially when they learned a third or even fourth language, for instance, like English or any other language, what would be your prediction for the results? So more languages equals in even less mental effort?
This is also interesting. So normally the studies being undertaken are stop at 3 languages, so at maximum. And at the moment, I don't know of any studies which study like children that are able to speak 4 or more languages fluently. So one important point here is that we talk of children who are really capable of speaking languages fluently on a daily basis. So that would be also a challenge to find those children that speak like 4 or 5 languages fluently. Intuitively, I would say that at some point there won't be any benefits in effort. But yeah, like when you speak at least one further language fluently, then that would be you could benefit from this.
Yeah, very cool. Thank you so much. So I think now it would be time for the last speaker in line, which is Gustaf Gredebäck from Uppsala University, holding a chair in developmental psychology, and talking about his studies. So Gustaf has published more than 100 papers since his PhD in 2004. And specialized in eye tracking, social cognition, and experience-dependent processes in early life.
Thank you for having me to come to this and do this presentation. I really enjoyed all parts of this conference so far. So my name is Gustaf Gredebäck, and I've been doing eye tracking for a long time. But what I thought I would sort of focus on today, not just to talk about very different things, is particularly how eye tracking data can be used to look at individual differences in small children, and when it maybe does not work so well. So that's sort of the goal. So I'm afraid it's going to be, I hope not too chaotic, but slightly chaotic in the sense that I'm going to go through many different studies, but it's basically one study, but many different papers and many different paradigms, but just to show from our side what has worked and where we found there to be problems. So that's sort of the goal to some extent. Let's see how it goes. So we start, no, leave the webinar, not good. I pressed something. Let me see.
It all works well. So we see now the presentation and also hear the sound.
Perfect. Okay, it just disappeared from my screen. But so we started the study in 2012, where we wanted to follow children longitudinally. So this is 120 kids that we follow from 6 months and up until 36 months, and they're now in school, and then we're assessing their sort of school grades and the number of friends they have and things like that. And at some points we have a lot of questionnaires from the mothers even before the children were born. We look at attachment at some point and many behavioral tasks, but what we do have is a lot of different tasks looking at eye tracking. And this was something that was new to us. So we have at a single session, say at 6 months, children spend the whole day in the lab. And the eye tracking part is built up into 4 different blocks of eye tracking tasks that are intermixed. And by using this approach, we're able to assess something like 20 different cognitive or social abilities in infants in a single sort of run. And that has been very exciting, but way more challenging than I thought, actually. So all of the tasks I'm going to talk about today works very well in classical experimental group level studies. It's just that some of these things work really well with individual differences, just other things do not. So I'm going to give 3 examples of sort of general topics that we have used this data to explore. And one is how children understand other people's actions and action goals. We're going to look at gaze following and statistical learning and what that provides for young babies. And as I said, some examples of things that where we found challenges and we really had to think ourselves about why that is the case. And we'll talk about some global measures and what I would have done differently if I would have done a study focusing on individual differences longitudinally with eye tracking in infants today. So if we start off with action perception. So here are 2 different types of events that we have worked with a lot in my lab. And the top one here we call action prediction or action anticipation. And it's basically infants are watching a sequence of manual events. In this case, there's a woman eating, but it could be someone reaching for a ball or putting a ball into a bucket or whatever it may be. And what we can see generally from many studies is that the ability to anticipate these actions by looking at the goal of the manual action before that has happened is something that babies are really good at, and it sort of emerges along with their own ability to perform the same actions. The lower part here is called action evaluation, and that's when we perform an action sequence, or babies observe an action sequence, ideally between 2 individuals, and something odd happens. So in this particular case, they're building a block tower together, and one of them holds up their hand and asks for the next block, and instead the block has been put on their head. That would be an odd action, and what we see then is that pupil dilation that many people have talked about so far. This is something that we've been very interested to understand how these processes sort of interlink with each other, the ability to make an anticipation and to react when that anticipation is incorrect. So here are some studies that where we worked with that. But with respect to this particular topic, just if we just look at this data a little bit, what we can see, there's a lot of dots here, but the top figure shows really that there is a correlation on a group level between the ability to make predictions at 6 months and the ability to evaluate the strangeness of an action at the same age. So an infant that makes many predictions, then there is a higher tendency for that child to react very strongly when something happens that's sort of outside the normal script. We can also see that there's a correlation between action evaluation at 6 months and action evaluation at 12 months. So there is stability to some extent, even though, as you can see here, there's a lot of variation between individual babies. But what becomes interesting here is that is the lower left side, where we look at the ability to make predictions at 6 and 12 months, 10 months, sorry. Now it would be, at least our assumption is that those would correlate, that there would be stability, that some children would be better able to make predictions, and that would be something that would hold over time, at least over these 4 months. But what we can really see that at 6 months of age, kids are really, really poor at making these predictions in this particular context. About half of the children make these predictions, half of them don't. But when we go into 10 months, pretty much all of the children make these predictions. So that's sort of, it makes sense, but it's really hard to look for long-term stability in eye tracking data when there's such a qualitative shift in the way the children understand or perform on something. But using this, we're able to see anyway that we also have other tasks in this longitudinal study where we measure motor development, for example, and the ability to reach and control their own manual actions. And what we can see is that that ability feeds into the ability to make predictions or anticipate other people's actions goals. And that is but from the data I just showed you, there's a strong association between the ability to actually make evaluations as well. So this action evaluation and action prediction is something that we refer to as internal models. The ability to form an hypothesis about the world, in this case about other people, and try to anticipate the goal of other people's actions. And when that is failing, to be surprised and use that information to update their own expectations about the world. So an hypothesis-driven process from the child's perspective. And what we can see when we follow children over time into 13 months and above is that the individual differences in that internal model seems to predict both executive functions and prosociality later. So children that are better able to sort of make anticipations and evaluate those anticipations, whether they're correct or not, tend to be more pro-social and have better, at least inhibitory skills as a component of executive functions. So I think that's something that's worked out fairly well in terms of the methodology of using individual difference approach to eye tracking data. I'm going to talk about why I think that's the case later. But another example that worked quite well for us is in terms of gaze following. And this is a sort of something that many people use. Here you have a person looking straight at the baby. And then if this would be a movie, she would turn and look at one of these two objects. And what we're interested in seeing if the baby makes a saccade to the same object that she is attending to. And this is a phenomena that we can sort of track down to 4 months of age. And over time, it develops and continues during the first year, pretty much to sort of mature and stabilize. But what we've been interested in this particular study are two things. One is, can we find individual differences in the tendency to do this, and where do those come from as a starting point? And this is a terribly complicated graph, but let me just boil this down to you guys. So when we just look at basic correlations, not a complex model like this, but just the raw correlations, it looks like gaze following at 6 months correlates quite strongly, around 0.4, I think, with gaze following at 10 months, which is all fine and good. But when we put it into a more complex model where we look at different properties of the relationship between the mother and the child, or the mother herself, in this case, attachment or depression in the mother, we really can see that those factors influence both the onset time of gaze following, but also how it develops over time. And in this type of slightly more complicated model, the association, the stability in gaze following really sort of disappears. It doesn't really seem to be that it's not stable enough to track individual differences over time. It's rather other factors that seem to drive both the onset and further development of this. So the picture is quite more complicated than we thought. And this is also from the same study. And what we've done later with this is to compare this in different cultural contexts. So we did this in the lab in Uppsala, and then we went to Bhutan to do the very same study there. And interestingly, what we can see is that in Sweden, when the mothers feel not so well due to depression, or that there is an insecure attachment between the mother and the child, that really has a negative impact on the ability to make these gaze shifts in the child. In Bhutan, the children are equally good at following gaze, and the mothers are, if anything, feel worse. They're at least to an equal degree or slightly more depressed than the mothers in Sweden. But there we don't really see that effect. It seems like there's no transmission, not that, as we can detect anyway, transmission from the mother to the child. And this is something we're moving along now with further studies in Bhutan and Zimbabwe and Sweden, where we want to think about, or we are thinking about the society in which the child is raised, and the cultural values around the family, to see if there's something that is buffering with respect to more collectivistic societies where you have more people being involved, and the parent-child dyad is not so alone as you can find many cases in Sweden. This is another area where I think this has worked fairly well for us. The third area, that's where sort of things become more complicated, I think. And this is respect to statistical learning. Here are just 3 different tasks that we and others have used in just classical experimental work from before. On the left side is what we call an associative learning task. There are basically 2 areas of interest. In one of them, there is a small object, there is an animation and a sound. The other one, there is another animation and a sound, and that goes one after one, like this. And then there is a test phase where there's just a sound. And we want to see to which of these 2 areas the children are looking. And the second part is a probabilities task. And I'm going to show that, I think, on the next slide, because I think it's really neat. But basically, there's a lot of balls being put into a container, and then we sample from that, and we can see if those samples are surprisingly or unlikely or very likely, depending on the properties of the population. This is again something that children from 6 months of age are pretty good at doing, usually. On the right side, there is what we call the visual sequence task, and that's just an object, several different objects appearing in different locations in a sequence. And what we're looking for are infants' abilities to predict the upcoming event. So if they're really good at this, they're going to be able to keep track of these sequences in a predictive manner, which some babies are doing, but a lot of them are not. So here's that probabilities task, which I just think it's, let's see. So when we present this to small children from 6 months of age and upwards, we can see a very interesting pattern of looking behavior. So if the outcomes are very unlikely, they tend to look more at those than others. But if they are much more likely, then they also focus on those compared to other stimuli. So we really get a U-shaped function where we can't say something simple as they always look at the most surprising event, or they always look at the most reasonable one. It really depends on the properties, statistical properties of the samples that we pull out. And this is we've replicated several times with different age groups. So we're pretty comfortable that there are these U-shaped functions, but there's just no linearity in the development related to eye tracking. I guess that's sort of one of my main points here. So looking at this, and this is a lot to take in, I guess. But if I sort of walk you guys through this, what we can see that there are, if we start with something like, so later we look at the statistical tasks, and then we compare it to later language. So we have receptive and expressive vocabulary as our outcome in this particular study. And what we can see that the visual sequence task, the one with the 3 different sort of objects to anticipate or predict, we can say that ability to be able to make those predictions and see those patterns is something that is very strongly related to receptive vocabulary, which we found to be extremely exciting. But looking at these associations, they are surprising. So the visual sequence task at 10 months has how babies perform there is related to how the same babies perform at 18 months in a similar manner. The ones that are good at this are also good at 18 months. And that is associated with a large receptive vocabulary. So that's all fine and good. But at the same time, there is a negative association between visual sequence and 10 months and receptive vocabulary at 18 months, which again, it's really hard to understand how these can sort of flip in that particular way. We can also see that there are associations between associative learning and expressive vocabulary, but the ability to pick up probabilities, for example, doesn't seem to have any association with language the way we conceptualize it here, at least, which is surprising to me, particularly as we know that children or infants are very good at picking up these probabilities. But it doesn't really seem to help here. So these things all work, and it's taken us a bit of time to figure out this, because some of the tasks we've had problems with, and it goes back to some of the things that I just showed you. But here are three sets of stimuli that we've used that we are less sort of certain with whether they work or not. And this is the thing we really thought would work. So this is just biological motion. If I would animate these, the dots on the left side would sort of create a human clapping their hands. And on the right side, it's just the same individual inverted. And from what we know from the literature, children are able, or infants are able to pick this up. And they should, from a prior non-eye tracking work, just look at the upright biological motion. But they don't systematically. Some do. Some focus very much on the inverted, and for some we just can't see a difference. We have another stimuli where we also have dots, and one is just random dots. Each dot moves slightly differently, and on the other side, a certain percentage of the dots drift in a certain way. So that's a random dot pattern. And that global motion that exists on one side should really attract children's attention again. But in our eye tracking tasks, it doesn't. We also have a task for approximate number system, where we have just on the one side of the screen, there is a continuous bombardment of dots that are equal in number. And on the other side, they change, say that there's 12 dots, 6 dots, 12 dots, 6 dots. In that case, the literature really suggested that babies should attend to that changing stimuli if they're able to sort of approximate and detect that there are differences in numbers. We do get some results, but it's quite a lot lower than what we would expect from other types of studies. I think what's really happening here is that on the one hand, the literature suggests that you should focus on the things that has more information and is more interesting and is psychologically meaningful. But there's also noise on top of that. And what we can see that most children do this, but we have a certain portion of children that tend to do quite the opposite. That, wait a minute, this stimuli I don't get. This is unusual. This is our interpretation of what's happening, of course. We have no idea of knowing that, but see some children that are sort of systematically just oriented to the thing that they shouldn't pay attention to because there's just less information there. So when averaging these out, we do get some sort of effect sometimes, and other times on average, it just doesn't turn into anything. But it's particularly difficult to make individual differences of this. Because if you have a U-shaped function and you put it together, it's really hard to understand what is normative and what is good in this case. Is it better to pay attention to the interesting, or detect the interesting, disregard, or the meaningful, disregard it and look at the thing you don't understand? It's very unclear. And it becomes actually extremely difficult at all to just create any index that captures individual differences somehow. So in all of the studies we have, in all of the stimuli we've had in this study, I would say that the things that have worked less well are things but nothing is surprising. There are no instructions. There are really no clear gains. It's just but if there's anything, on the other hand, the things that seem to work much better are things where things happen quickly, like when someone is reaching for an object, or there's something that they need to anticipate. They need to keep up, and there's a clear, we know what's good in the sense that if they want to pay attention to the stimuli, they need to be quick. And if they're not quick, they're falling behind. In those cases, it's much easier to talk about meaningful individual differences. I think also pupil dilation has been something that's worked really well in terms of getting stable individual differences, which has been demonstrated before as well. And to me, there are of course different versions of pupil dilation, which was also discussed before, where it's going to be cognitive load, arousal. But the things that's worked best, I think, for us are the things that almost, where the children, there's something really odd happening, and that surprise reaction we get there seems to be very stable and capture meaningful individual differences. So those are two things that sort of, if I would do this again, but I would really focus on things where we really can be more clear with what we expect from the child. Particularly with eye tracking, where there's no cost to look at different parts of a screen. You can just go back very quickly, and a child can also. So then it particularly becomes important to put some instruction or some task demands, I think, for the child. But I have two more things that we've been exploring recently that I also think we are at least going to use more in the future for individual different studies. One is a PhD student here in Uppsala and in Leipzig, Sing-Fen, have been looking a lot at taking all the data from these many eye tracking tasks in several different ages and try to find global attention measures. And one measure is the simplest one ever, but it seems to be very stable. It's just the look percentage, the thing you get out from the Tobii just recording where it says that you have 25% data or 50% data or something like that. Just over the very different time points that seem to correlate very strongly. So some children do pay a lot of attention and other babies do not. Another thing that she did is just looked at the mean, plotted all the fixation for all the children. And what you can see over multiple tasks, that there seems to be like this by a particular distribution with a two-peak distribution, bimodal distribution of fixations. You have either short fixations or long fixations. And calculating the ratio of short fixations out of all fixations seem to also be an attentional measure that seems to be very stable across ages. And that is something that she used to go back into the data and try to see if that could be used to sort of understand actually in both directions, relating it to executive functions, but that's another story altogether. In this case, relating it back to properties of the mother and her early experiences. And there she is able to demonstrate nicely that early exposure to trauma in mothers, even before the child is born or even conceived, that trauma seemed to have a huge impact on the child's attention, both at 6, 10, and 18 months. And it's also related to maternal anxiety during pregnancy, in particularly week 17, where we can see that all of these factors together really has an impact on the attention of the infant. And when we really have stable attention measures, I think that's the only time that it makes sense to do this analysis. And I think she nicely captured the fact that there are ways to using vast amounts of eye tracking data to sort of get stability. And then when you have stable measures, try to see how that relates to different components around the child in different contexts. My last thing I would add here is that we've started to be more explicit with instructions for the child. And this is something that we've been very much inspired by others. Bergelson and Swingley, who used this task to have two images on a screen, an apple and a ball, and then say, look at the apple. And then children from 6 months tend to be very focused on orienting toward that object, and you know, they sort of understand that linguistic marker. And a PhD student of mine working in our group, Anton Gerbrand, have been using this to look at numerical properties. So you have dots and then say, look at 3. And then there's that instruction that it's actually meaningful to look at the 3 objects, not the 1 object. And he's able to track that development quite nicely and suggest that, just to sum it up very quickly, that infants or young children know numbers much earlier than what we thought before, which is really exciting. And I think that idea of telling the child what we want them to do at a very early age is really neat, and I think something that at least we will try to explore more in the future. So that's all. My phone is ringing, so I don't know if you heard me there at the end, but yeah, that's all I had. Thank you very much.
Thanks a lot, Gustaf. So yeah, we just heard that something is happening with the voice, but we didn't hear anything in the background. Okay. So good. Yeah, we are yeah, super fascinating what you all can get from children at a very young age, even though you can't speak to them or like send them a questionnaire and ask them for feedback. So that's always super fascinating to see. What I would like us to do now is, since we have a couple of questions that might be interesting for the entire crowd, to get everyone kind of on stage, so that we can address that that question to everyone, which would be very interesting. So please, everyone that is still here with us from the panelists, come on stage, so we can answer that one. Excellent, thank you. So I think one thing that we've seen in many talks, or well, I think in all of them, is that the question was asked about the optimal sampling frequency for pupillometry, if there would be something that you would recommend. So maybe we can go around the table to
You want to point at someone?
yeah, maybe that's a better idea. I agree. Yeah, maybe you start, Gustaf.
Well, with respect to pupil, it I think depends what you want to do with it. But generally, just if we're looking at pupil dilation, the normal type of sort of response to an event, or as an indicator of cognitive load, I would say it doesn't matter, because it's a change over seconds. So we've done this reliably with 45 hertz, 60 hertz, 200 hertz. I don't think it matters at all, actually, from my perspective. Something that we've done a lot is to just provide a flash of light and look at the adaptation of the pupil to that light and use that to predict autism, for example. Then you really need a high frequency, because that's a very rapid response. But that's something else altogether, I think. But that slow transition is, yeah.
What is your experience on that, Julian?
Well, we've used it so far together with Robert, who is the expert on that issue for our sample, and we related that also to autonomic arousal, the pupillary light reflex. And for me, it's really hard to answer if it's really a useful measure that you can use. Well, from my impression, but I'm not an expert, that you always get into discussion what's really measured by pupillometry, and you can get into really fights depending on what reviewer you have, what you're measuring, what you're not measuring. So you probably have to be really cautious, but using it as your own dependent variable, I don't know, I wouldn't be that convinced at that point of research or knowledge, but I'm probably not expert enough. But right now we are quite cautious in using it.
I have a question for Gustaf, actually. You mentioned that you've used different eye trackers for measuring pupil diameter. Do you ever find reviewers or who push back if there are systems that have bright versus dark pupil, or do you ever find any differences in the data if you're using bright versus dark pupil technique, particularly with our Tobii Pro systems?
No, we haven't. But I mean, I think when we started doing that in 2008, and by then the systems had one or the other, or you sort of have to, it's like you have to switch between one or the other. I think no one was aware of these problems at that point in time. I mean, now they flexibly do quite well, all of them. So I don't really think it's a technical problem anymore, but it certainly was. I just think none of us paid attention to it or knew about it.
Okay, so if you were using one of our modern systems that switches between bright and dark depending on the participant, we wouldn't find any differences in those pupil diameter estimates between groups of either using bright pupil or dark pupil?
We haven't systematically checked that in with your new systems.
Okay.
I wouldn't know. No. Robert might know.
Yeah, maybe you can also jump in with your experience when it comes to sampling frequency and pupillometry.
So I have a very hangry child next to me. I don't have anything to add. So all the things that were said, I completely agree with. And we've also never systematically compared bright pupil tracking to these automatic systems, but never found any issues really, anything that would concern us.
Okay, that's good to know.
One question would be more targeted towards using eye tracking glasses and the use of it. And so the question was, if you use, in case you use it, in any additional ways of assessing the quality of the calibration after using the calibration with a card, is that something that you consider doing, or like what do you do then to make sure that the calibration was done properly and the quality is right? So maybe we start with you, Robert, in case you've done that. So have you had some experience with the glasses, or maybe the video froze?
So we've always followed the a paper that was. Mm-hmm. Can you hear me okay again?
Yeah, we can hear you. No,
so we always did a post-calibration recorrection, as it were. So we
must be having some technical timing troubles.
Yeah.
If you want, I can jump in and tell what we were experiencing. I mentioned that briefly, that we had problems when was not so much head movements, but when children had rather smaller heads, that the glasses were moving, and then afterwards we had a shift. And the problem is in the data where you saw that they were not accurate anymore. The calibration did not work. The problem is that you're pretty much unable to find out when the shift started, or when the shift or the systematic shift in the calibration, when did the glasses move during the experiment. So what we basically did is between trials or between the tasks, we instructed the participants to look again at the fixation points. So afterwards you could see, when you told them, please look at that dot here at that wall, you see that it is, you have an offset, then you assume that you have an offset in your calibration. But the problem is then you don't know when it happened, and it was a big problem where you kind of have to, especially with glasses, you have to kind of decide by hand correction whether a particular fixation is in your area of interest or not. But that is a problem. Another problem that we had, we used for the study that I presented, used the SMI glasses, that when you have an object that kind of, when you have more or less distance, so you have a shift in distance between you and the object, then the calibration doesn't work. It works pretty well when the interaction partner is, or the object is at the same distance through the entire experiment. But if like a parent comes closer, then the calibration doesn't work anymore. There is a specific term for that, but I forgot what it was named. Like parallactic.
Parallax correction.
Yeah, genau. And that we had some problems with the SMI glasses with that, and we from then on we only did experiments where you had a stable distance between participant and object.
I think you also touched upon another question that was asked in the chat, is like, if you would think that working with children at the age of 5+ would be recommended, or what would be kind of the threshold, or what was your experience with the children and wearing glasses, and if you would calibrate them in a different way compared to adults?
Is that a question to me or no?
Yeah, or to everyone who used the glasses. So I don't know if you use them, Gustaf, for with children yet. No. Okay.
We used them also in a kindergarten study, and it worked pretty well starting age of 4. But after that, it was really hard to get children to be compliant and not taking off the glasses, because as I mentioned before, with the glasses that we used so far, you really have to be cautious that they don't move. And we had a pilot session with a child that was 2 to 3 years old, and he was rubbing off the glasses all the time. So that was not really doable. But at age of 5, I'd say they work.
Okay, cool. So I guess no more questions from the chat, at least from what I can see here. Yeah, seems like. All right. So we got really good feedback from different people saying that they were really impressed by the content. And what we will do definitely is bring up all the different talks online later on, so that everyone that registered for the webinar has access to it. Thanks a million from all of you. Yeah, just got another comment, like this was a wonderful webinar. So thanks for that. And yeah, I think it's great that we had the time with all of you in one virtual room. So traveling is not an issue, and could talk about, yeah, how to work with kids and eye tracking all together. So thanks a million, everyone, for joining and presenting their study. And yeah, hopefully we will see each other soon again, also in person then. All right.
Awesome.
Thank you very much.
Thank you, everybody. Good job.
Bye.